I'm Lubbe, and today I'll be talking about the states of matter, specifically the solid state. And what we're going to do is we're going to talk about the different chemical bonds. Covalent not so much in this instance, but I will be comparing specifically your metallic bond and your ionic bond and the contrast between them. Alright, and also their physical properties and how that is explained by the chemical bonds. So firstly we'll look at the ionic bonds. I labeled them already there. Ionic bonds. These consist of your ions, positive, negative ion. We know from the periodic table that positive ions come from metals. It could be alkali earth, your group 1, group 2, or the transition metals, the quintessential metals in the periodic table. They all give off electrons, whether it's one or more, and then they become positively charged, positive ions. Then your non-metals become negatively charged ions. Alright, so typically an ionic substance, metal, non-metal combined. Alright, so for example, sodium chloride. Now we know we write the formula unit like this, NaCl, one of each, but we know it's not a little molecule, one sodium, one chloride. We know that it is actually a whole set of ions, positive sodium, negative chloride, positive sodium, negative chloride, and they fit together because they are attracted, because their opposite charges causes an electrostatic attraction, and they end up forming this crystal lattice that is cube upon cube upon cube, depending on how big the crystal of salt is that you have. So, because your ionic substances have this very, very strong electrostatic attraction between the oppositely charged ions, these substances tend to be very hard, very strong, but they are very brittle. They will not take a blow. They are like cookies. If you take a cookie like this, if you don't press it hard enough, nothing's gonna happen. But if you press it hard enough, it breaks. It does not change shape. It does not dent. It just snaps in half. That is a crystal. That is an ionic crystal. Alright, so they have their other traits as well. High melting points, high boiling points. They tend to be soluble. Not all of them, but mostly. But the main thing, the main contrast between your ionic bonds, metallic bonds, is that ionic substances are brittle, which gets us to metallic bonds. And now we're going to go back to the periodic table just for a moment. The metallic bonds, again, all of your elements that are metals, group 1, group 2, transition metals, and then a few on this side, as well as your heavy metals lower down. Your metallic properties can be most obviously seen, like I said, in your transition metals. Those are what you'd say the quintessential metals. Their metallic properties are very pronounced. That is, metallic properties such as hard, strong, very dense. They tend to have very high melting points, very high boiling points, also all because of their chemical properties, which you're going to take a look at again. The metallic bonds consist of positive ions all arranged in a perfectly regular, rigid structure, a metallic lattice really, and in between them is what is called a sea of delocalized electrons. So your outer electrons, not all of them, but your outer shells, the electrons tend to come loose. Let me just for an example there. They go out of their orbit and they enter this sea where you can no longer tell which electron or which set of electrons even came from which specific positive ion. They are all shared, they all move in between in 3 dimensions, and that is our explanation for where the traits, the physical properties of metals come from. They are very hard, they are very strong, they are excellent conductors of both heat energy and electricity. In fact, I often, for a visual demonstration, I like to think of metal as a bit like press stick. This is not to say that a press stick is a metal, but press stick can be seen as a visual kind of demonstration of how metallic properties work. We hear terms like malleable, ductile, high tensile strength, and they kind of get interchangeable. We think they are the same thing, but they're not really. Malleable, for example, meaning that, imagine this is a piece of metal. It can be squished, it can be beaten. In fact, it can be beaten into a flat sheet if you apply enough force. Obviously, it takes a lot more force than what I just applied to the press stick. Ductile means you can roll or twist it into a long wire. This is why it's so easy for us to make wires out of metals. We make wires out of copper. We don't make wires out of salt, ever. Again, it will break. It's not going to take it. Alright, now the reason why we can do this with metals is because of all those delocalized electrons. And also because if you apply force to a metal, the ions will move. Let's say they move that way, and these will move this way. They move out of position, but it's very difficult to break that piece of metal because of the extremely strong electrostatic attraction between the positive ions and all of these delocalized electrons. Whereas with an ionic substance, you apply just enough pressure to strain the substance, and you will have what? You will have positive and positive next to each other, or negative and negative next to each other, and they repel. And that's the reason why, I'm going to take out my cookie again, why crystals tend to have such a clean break. They just split in pieces, there's no dent, there's nothing. Metals, on the other hand, are very, very force resistant, and we can make them even more force resistant by making them into alloys. I'm going to copy this small picture and make it a little bit bigger just so you can see more properly. Let's say we melted a metal, we made brass, 90% copper, 10% zinc, I believe. Different elements, different sized atoms, which give us different sized ions. Since these ions are different sized, they don't roll over each other as easily as with a pure metal. So you apply the same force, but it is more difficult for the ions to roll over each other, which means it's more difficult for the metal to dent. That is not to say that a piece of brass, a piece of bronze, a piece of constantan, steel, whichever alloy you're talking about, there are so many of them. It is not to say that they are indestructible, obviously not. It just takes a lot more force to move those ions because there are different sizes. And then once you get into different types of alloys, we talk about interstitial and all of that. Sometimes they are smaller, sometimes they're bigger, but point is they are not all the same size, so it's more difficult for the ions to go rolling over each other. Alright, so that is your ionic and metallic bonds. Now one quick last subtopic before we finish up. I said we're not going to go into that much detail on covalent bonds and covalent structures, but I did want to discuss the 3 allotropes of carbon because they are so vastly different, especially in terms of their traits. Firstly, we have diamond. Right, diamond will have your somewhat pyramid shaped molecular structure if you were to zoom in on molecular level. And why is that? It is because every carbon atom is bonded to 4 other carbons. We know from the valence structure of carbon that it has 4 valence electrons. That is the maximum amount of bonds that it can have, and every one of those valence electrons is bonded to another carbon, and then each one of those carbon atoms is bonded to another carbon atom, which ends up giving us this very sharp pointed pyramid shaped molecule, and it just goes on and on and on for however big your diamond is. Diamonds are very hard, they are very strong, they do not conduct electricity at all because there are no free electrons, no charge carriers available. All the electrons, all the valence electrons are occupied. That explains why diamonds are so hard and strong, but it also explains why they are brittle. Because they're not metals. In fact, the allotrope of carbon that is closer to metal in terms of property is graphite. Now graphite, every carbon, as you can see, they form these layers of hexagonal sheets. And every hexagon consists of 6 carbons, not 6 all bonded together, that would be impossible, but each one of these carbons being bonded to 3 other carbons, like this. Which begs the question, where did the 4th electron go? Every carbon has a 4th valence electron. What is that electron doing? It's hiding. It's not actually hiding. It is in this tiny little cloud between the layers. Every carbon donates 1 electron to this cloud that falls between this layer and the next layer. So this layer will have every carbon bonded to 3 other carbons, and then its 4th valence electron is in the cloud that connects the layers, which explains why graphite is soft and not as durable as diamond. It is so soft we use it in our pencils. We literally slide millions of layers off every time we write something in a pencil. Graphite is also capable of conducting electricity because of those free electrons. It is not as good as a metal. We're not going to make wires from graphite. We make wires from copper, which is a metal. We make wires from constantine, which is an alloy, nichrome, which is an alloy. We'd never make wires from graphite, but we can make very weak resistors from graphite because it's so able to carry electricity. And then one more quick discussion, and I'm going to show you this on my screen. So your 3rd allotrope of carbon, carbon nanoparticles, fullerenes. Firstly, you get the Buckminster fullerene C60. It's also known as the buckyball. It literally looks like a soccer ball. It's got 60 carbons bonded together in little hexagons and pentagons, and it is often used to trap atoms or molecules of other substances. Then we have the nanotubes, that are these long cylinder shaped tubes, often not really drawn to scale because the length can be literally millions of times as much as the diameter of the tube. It is essentially like one layer of graphite rolled up, and they are very strong. When you hear about carbon fibers, those are basically made of nanotubes. And then finally you have graphene, that is a single flat layer of graphite, and it's extremely flammable but also extremely strong. It is basically said to have exaggerated versions of the traits of graphite. So those are the 3 the three types of fullerene that fall into the third allotrope of carbon, which I just wanted to show as a demonstration of how, again, how versatile carbon is as a pure substance, as pure element, which is not even to enter the discussion of organic chemistry with all of the carbon compounds, which, like I said, would entail a whole discussion on covalent bonds. So that basically brings us to our conclusion as we compare the physical properties and the reasons for those physical properties that you get between the different states of the different solid states of matter, ionic substances versus metallic substances. So I hope that this has made things simpler and more visual, I suppose. If we think of metals again as being ductile, you can stretch them out if you apply enough force, of course, and ductile, malleable, all of that, whereas your ionic substances can take absolutely none of that punishment. So I'm Joe Lubbe, and this has been a chemistry lesson.